it is not possible in this Dirac equation that we have now. Because you see that here in the rest frame, the upper and lower compounds must be equal. So if you set 1 to 0, then the solution will be trivial. Now, one case where we know there is, so when this line of argument will break down is for massless particles, right? For massless particles, there is no notion of the rest frame. So this case should be considered separately. And there, we will see that we can really consider only left and right fermions. So in other words, we can write the Dirac spinor as a compound of two-dimensional spinors. And so these spinors are called Weyl spinors or chiral spinors, and they're usually associated with left and right-handedness, so that we will understand why. So we need to understand why. So let's now consider the massless Dirac equation. And again, so this way of solving it then simply will not be possible, because at some point we assume that there is the rest frame, right? So these solutions, they assume that the particle has a rest frame. If you put m to 0, then this solution will just go to 0, and it doesn't get the right answer. So it doesn't have a nice massless limit. So when we have 0 mass, then in the Dirac equation we have zeros off the diagonal. Sorry, we have zeros on the diagonal, and off the diagonal we have some combination of Pauli matrices. So we see indeed that for the massless fermions, the left and right components of the spinor satisfy two separate equations. So E minus plus P dot sigma chi left or right is equal to 0. Yes?
When you say P dot sigma vector, do you mean Px sigma x plus Py
sigma y is at sigma z. So this is
including P0 then.
Yeah, I included it in. This is non-relativistic. Well, I mean, space and time are treated separately. Sorry?
So this is P3 vector?
P is, yes, I'm sorry. This should be written as an arrow. Here, you can write this in terms of this generalized sigma matrices defined over there. But let's just stick with these three-dimensional notations, non-relativistic three-dimensional notations. Okay, so again, this has a form of matrix acting on some vector giving 0. So this matrix better have a 0 determinant. And the condition for that is the mass shell condition for a massless particle. So namely, this has solutions only when the energy is equal to the absolute value of momentum times the speed of light, which is 1. And then the equation simply tells us that what? Well, we can divide by the absolute value of momentum then. So let's then define the unit vector in the direction in which the particle moves. And so the equation simply means that n times Pauli matrices over 2 times chi left or right. And this equals to plus minus 1/2. So the physical meaning of this equation is very simple. It just tells us that the projection of the spin, so this is the spin operator. So the projection of particle spin on the equation, on the direction of its motion, is equal to plus or minus 1/2. So it's plus 1 for left-handed spinners and minus 1 for right-handed spinners. So this combination is called chirality. Or, well, it's called helicity. It's n times times spin. So for spin 1/2 particles, spin is just sigma, is represented by the sigma matrices. So the Dirac equation for massless particles tells us that the left components of the spinner have positive helicity, and well, the helicity is equal to 1/2, but it is positive for left components of the Dirac fermion, and is equal to minus 1/2 for the right-handed fermions. Okay. So if you think of spin as sort of something that so if you think of electrons as spinning as a spinning I don't know, well, that spin is associated with some rotation of an electron, then with the same sort of cartoon way of understanding spin, the massless particle corresponding to the left-handed spinner so would then rotate let's see, its projection of its spin should be positive in the direction of the motion, so it should rotate clockwise around the axis in which the particle moves, and then for the left fermion it would rotate counterclockwise for the right, for the right spinner. So helicity simply tells us that particle is either left-handed or right-handed. So it spins in a particular way around its direction of motion. So what? Something wrong with these pictures? Anyway. in that frame. For a massless particle, that's impossible. You can move faster than light. So it will always move in the same direction, whatever frame you choose. Therefore, helicity is Lorentz invariant for a massless particle. So there is a third way that is also useful, and that is based on introducing a fifth Dirac matrix that is just a product of all four matrices multiplied by I. So explicitly, this matrix is given by the diagonal in this block diagonal form. It's equal to -1 plus 1. And so we can pick up the upper and lower components of the spinor by acting with what is called the chiral projector. And then this just eliminates, this projector eliminates half of the four-component spinor. So after the chiral projection, the spinor will have only two components, effectively. So this is called chiral projection. And now, well, we need to understand if this is Lorentz invariant or not. So the way to see that it is Lorentz invariant is to notice that gamma 5 can be written in a less transparent but equivalent way. So we can contract the four gamma matrices with the epsilon tensor. And the claim is that this is just equivalent to the form here. Well, I don't know if it's immediately obvious to you, but the way it works is that, okay, this will be a sum. So the epsilon tensor has 4 factorial non-zero components that correspond to possible so it is non-zero only when all the 4 indices are different. So it will correspond to all 24 permutations of 0, 1, 2, 3. And so the matrices will be multiplied in all possible orders where with the alternating signs. But now all these matrices anti-commute. So they have different indices. So you can interchange them using the anti-commutation relations. And when we interchange the two, they will change the sign. So these signs are precisely the same as appear in the epsilon tensor. So all 24 terms here are actually equal to one another and can be reduced to this basic form if we use if we anti-commute the matrices. And so since we divide it by 24, this is the same expression. But this expression is manifestly Lorentz covariant because we contracted something that transforms as a vector with an epsilon tensor. An epsilon tensor is a Lorentz covariant quantity. But it is, you know that this is it's not a tensor, it's pseudo tensor. Meaning that it is invariant under Lorentz transformations that are have positive determinant. So if the determinant of the transformation matrix is -1, then this will also change sign, okay, upon the transformation. So one example of these transformations are parity, well, is the parity transformation. So when we change the directions of all spatial axes. Okay, so this transformation, well, it is part of the Lorentz group, but under this transformation, so the determinant of this transformation is -1 and not +1. So under such transformations, gamma 5 will change sign. So it will behave as a pseudoscalar, not as a scalar. And therefore, what we are doing here, we are adding 1, which, well, is frame independent, and a pseudoscalar. So this operation, it preserves all transformations from the Lorentz group that have positive determinant, but breaks parity. So it is not invariant under the, well, reflection of all spatial axes. Well, the reflection of all spatial axes, well, it's like, you know, interchange what really happens with how we would see it in the mirror, right? It's a mirror transformation. So of course, in the mirror, something right-handed will look as a left-handed object, okay? So indeed, the left component, left-handed spinors and right-handed spinors are interchanged by parity. So one of the reasons that we need 4-component spinors to describe electrons and positrons is that, well, electrons and positrons, at least free electrons and free positrons, they preserve parity. So they look the same upon, I mean, reflection of all spatial axes. But in principle, the laws of quantum mechanics don't forbid us to have something that breaks parity. And so the laws of nature are such that at some fundamental level, parity is really broken. So this, of course, since the equations allow for it, why should it be there? And particles that violate parity in the most transparent way are neutrinos, so which are described by 2-component fermions of this type. So neutrinos are intrinsically left-hand or right-handed particles. In fact, electrons and positrons also do not preserve, so they break parity by the way they interact, by the way they participate in the weak interactions. Yes?
So you just now mentioned handedness in the context of parity. We've been talking about handedness in the context of felicity. Are those distinct or same kind?
No, that's the same kind. So if you have, suppose you have something with positive felicity that rotates in positive, in the clockwise direction, in the clockwise direction. Then if you change the, well, the signs of all axes, it will be left-handed. It will, because, well, rotation involves the, so in a sense, spin is a cross product of, okay, angular momentum is the cross product of x and p. So x and p transform normally under parity, though they change sign. But their cross product shouldn't have changed sign normally, but it does because, I mean, it's the property of the cross product. And so is the helicity. So helicity behaves as a pseudo scalar. It changes sign if we change the direction of the spatial axis. Okay, I have to stop now, and we'll continue with this in the next lecture.